This lecture is going to be divided in two videos. In the first one, we're going to talk about multi-objective optimization with finite element applications. And following this video, in the next video, we're going to talk about meta-model-based multi-objective optimization with finite element applications. So the outline of the lecture is, as you see in the screen. First, I'm going to talk briefly about multi-objective optimization. You all probably know what is multi-objective optimization, but in case some of you may not know it, so I will give a very brief instruction on multi-objective optimization. Then by knowing multi-objective optimization, we can talk about finite element simulation-based multi-objective optimization. Well, usually we abbreviate multi-objective optimization by MOO, or we call it MOO, and then the simulation-based MOO is the abbreviation for simulation-based multi-objective optimization. Then I will talk about two applications of finite element simulations with regards to multi-objective optimization. These are the applications that I've been working on. Then in the next video, I will talk about meta-models. So I'll define what is a meta-model for you. We'll look at some different kind of meta-modeling methods. Then we'll know how we can integrate meta-models with SB-MOO. And by using this integration, we can talk about meta-model-based multi-objective optimization. And then afterwards, two industrial application or two engineering application of meta-model-based multi-objective optimization will be touched upon. So what is multi-objective optimization? Professor Depp gives a good definition of multi-objective optimization. You see here in the video, in the screen, the in existence of more than one objective function, the task of finding one or more optimal solution is known as multi-objective optimization. So it is obvious that when we have more than one objective that we need to optimize, then we call it multi-objective optimization. So here you can see a simple formulation of a multi-objective optimization problem. As you can see here, we can have several objectives. Here we can have M objectives, and each objective can be either minimization or maximization. Along with objective, you can have constraints. The constraints can be in form of inequality constraints or equality constraints. Here in this equation, you can see that you have J inequality constraints and you can have K number of equality constraints. It is obvious that your variable can also be bounded between two limits, upper limit and lower limit. So this is a general formulation of a multi-objective optimization problem. But let's look at a simple example of multi-objective optimization that you may face even in your real life. Imagine that you want to buy a car, so you go to dealer, and there are two criteria for a car. One is price, here you can see in the x-axis, and the other one is the speed of the car. And you can see the minimum and the maximum available cars in that, and also the speed in terms of percentage. So if the price is mostly important for you and is the only criteria for you, so the dealer will probably show you car number one. But on the other hand, you might be someone who's interested in speed, and the price is not important for you, then the dealer will show you car number two. So in single objective optimization, you will have one optimal solution. And in our case, in decision making for buying a car, it will be either car one or car two. But as you may know, this is not the real case in real world. So price and speed might be both important for you. So in that case, one extreme solution, these are the extreme solutions, will not satisfy both objectives. And optimal solution of one objective may not necessarily be optimal to other objectives. Then here in multi-objective optimization, we will have a set of solutions. So in multi-objective optimization, there is no one optimal solution, and there are a set of optimal solutions. And in our case here, we can see that three other cars, car A, B, and C, are between the two extreme solutions. So if price is more important than speed for you, you will probably select A, but speed may be more important than price, then car C will be your option, or they might have an equal weight for you, so they might both be equally important. Then you will select car B. So these set of solutions, these set of optimal solutions will create a front, which we call it Pareto front. So let's look at the approaches in solving multi-objective optimization problems. There are generally two approaches in solving MOO. The first approach, which we call it the a priori approach, where you have some higher level information at the beginning. So if you look at our example, our previous example in buying a car, so your higher level information is that you know that the price of the car is more important than the speed of the car. So you have higher level information. Then, based on that higher level information, you can transform your several objective optimization problem into a single objective optimization problem. And then you have several single objective optimizers, and you can solve this single objective optimization and find one optimal solution. There are different methods that use this approach, and classical methods, including weighted sum and epsilon constraints, are some example of these approaches. So the second approach is called the posteriori approach. Well, in this approach, you might not have a higher level information at the beginning of the problem. So for your example, for the car buying example, that's an easy problem. So you will have probably some criteria at the beginning, and you know which objective is more important for you. Then you have a higher information at the beginning of solving the problem. But for real world engineering problems, you don't know the nature of the problem, and you don't have that high level information. So you need to use the posteriori approach. Well, in the posteriori approach, you solve the multi-objective optimization problem by using some optimizers. And by using the optimizers, you will find a set of solutions. And then by having the solutions in front of you, then you can have a better decision-making process and select one optimal solution. So as you see, the difference between these two approaches is that for real-world problems, especially engineering problems, having the higher level information at the beginning of the problem is usually not the case. So you have to use the second approach, with a posteriori approach. And evolutionary methods are one of the methods that are really well suited for this approach. And genetic algorithms are one example of evolutionary methods. And two of the very well-known methods in genetic algorithms are NSGA2 and SB-MOO. So we'll see these names later on in the presentation, the SB-MOO algorithm. There are two goals that it has to reach. First of all, but let's look at some. Let's look at one criteria, one property of multi-objective optimization. This line, multi-objective optimization. So that's one of the. You have an additional space, and second, the algorithm should be able to find solutions that are uniformly distributed all over the other space. So if an algorithm gives you some solutions here only in this part of the line, in this part of the line, and not any solutions here and one solution here, that's not a good algorithm, because you as a decision maker, you can make better decisions by having all these solutions along the line. So that's one of the criteria of having a good optimization algorithm. As I said, evolutionary algorithms are very well suited for this kind of problems. Here you can see a test function. That's the ZD3 test function, and the dashed blue line is the Pareto front of this problem. And you can see that the red dots are random populations. So these populations are created randomly at the beginning, and through generations, they will evolve until they will converge to the Pareto optimal front. You see that the algorithm is able to find the optimal front very well. So now we know that what is multi-objective optimization, and we know we can use evolutionary algorithms to solve multi-objective optimization with step posteriori approach. But where does the simulation-based multi-objective optimization lie in this plot, in this diagram? Well, if the objective values are generated or obtained from running simulations, then we call that simulation-based optimization. So if we look at here, one of the optimizers, as I told you, was the SB-MOO algorithm. You could see here the flowchart of the algorithm. And the simulation will be placed on the fitness assignment of the flowchart of the algorithm. So the values for the objective function is found by running finite element simulations. So what is finite element simulation, or what is finite element method? Well, one basic application, or one very simple application that's mainly used for introducing finite element simulation is this problem. So you have a cantilever beam, which is fixed at one point, and it's free at the other point. And so you can put some loads on the free end, and you can see the beam will deflect. So if you want to see how much the beam deflects by applying the load, and how is the stress distribution within the material or within the beam, then you have to use finite element simulation. What you do is you model your beam in some finite element solvers. And you can see, why do we call it finite element? Because you divide your model to very small number of, or to a number of elements, small elements. And these elements are finite, they're not infinite. You can see each of these rectangles are one element. So you divide your model into a number of elements. And by assigning the boundaries here and the load on the other side, and by defining your material model into the software, so if you have a stainless steel, or if you have cast iron, you have the model for that, which is obtained from experiment, and you implement the model into the software, then you run the finite element simulation, and you will get the result like this. So this shows the stress on the fixed part of the beam. So you see how much load this beam can carry, and with what load it will deflect, and with what load it will break. Here you can see one simulation of finite element with a beam, it's the same beam. And that's the vibration simulation in finite element method. So that's basically what is finite element method. So now, if our objective is obtained by running the finite element simulation here, we call this problem, the multi-objective optimization problem, the finite element simulation-based MOO. So maybe the objective can be the deflection of the beam. So you want to put different loads. So the load can be your variable, and your objective can be the deflection. So in order to find the deflection for different loads, you have to run the finite element simulation, and you will get the deflection for each load. And then you can use that in your multi-objective optimization algorithm. So let's go back to our previous slide. So here we saw that the finite element simulations will lie in the fitness assignment part of the optimization algorithm. But now let's look at one real-world application of finite element simulations in multi-objective optimization. Well, the use of multi-material structures in automotive industry is widely increasing now. So here you can see in this picture, two different materials are joined together by adhesive in this picture, and here they are joined together by spot weld. So adhesive have several benefits over traditional joining methods, and one of the most important benefits is structural integrity. You can here see the structural integrity. This is the picture results, sorry, this is the results from the drop tests. So a load is dropped from height on these two structures, and you can see the deformation. So the same load, the same height, but you can see the different results. The adhesive kept the structure very well compared to spot weld. So adhesive has a lot of benefits over the traditional joining methods. Other benefits are the galvanic insulation property of adhesives, the vibration damping of adhesives, and also the sealing capacity. But in order to use adhesive in joining materials, we have to be able to simulate the joining methods. And for doing that, we need finite element method. And for having finite element method, to have an accurate finite element method, you need an accurate material model. In adhesives, there are two modes that dominate. One is shearing and the other is peeling. Here we can see how shear works. This is the adhesive in between, and these are the two different structures that are joined by adhesives. So the adhesive can be under shear load, or it can be under peel load. So we want to investigate how good adhesives are under these two loads. But in order to investigate that, we need finite element simulations. And in order to have accurate finite element simulations, we need accurate material model. But how do we get that material model for adhesives? Well, here in this figure, you can see a finite element model of an adhesives. On the top image, you can see a thin adhesive layer under scan electron microscopy. So here is the figure from a microscope, and here it's a similar figure modeled in finite element. The dark spots here and here are the minerals in adhesives, and the light spots here and here are the polymers. But in order to have an accurate model, we need to be able to determine the parameters of the material model accurately. So there are 9 parameters. You can see here the 9 parameters, or we call it here 9 variables that we have to determine. So the one with one are showing the polymer blend, or the variable related to the polymer blend, and the one with 2 are related to minerals. So there are 9 variables. But how do we find these variables? How do we find the optimal value for these variables? What we can do is we can run experiments. We can run physical experiments on adhesives and create or draw the stress strain curve. So by performing experiments and drawing the stress strain curve, you have an accurate stress strain curve which is based on physical experiments. Then you can run simulations, finite element simulations, and find the same stress strain curve. So if you want to have the simulation as much as possible near the physical experiment, you have to reduce the error between the two plots, the two stress strain curves. So the objectives here is to minimize the error between the two curves. ED shows the experimental curve, and ST shows the simulation curve. And as we said, 2 modes, the peel and shear mode, will dominate in adhesives. So we have 2 different plots, one stress strain curve for peel and one stress strain curve for shear. And we want to minimize the difference between these 2 stress from experiment and simulation. So this study has been done before by one of our colleagues here in the mechanical department. But in that study, what they did, they used a priori approach. So they just transformed the 2 objective optimization problem by using the product of these 2 into a single objective optimization problem. They ran an optimization problem and they find one optimal solution, which is a set of variables. So here you can see that the optimal solution that they have found is this red dot here. X-axis shows F1 and Y-axis shows F2, which is the shear mode. And you can see the lower, the better. It means that there are less error or lower error between experimental and simulation curve. So what we did was we wanted to do the same optimization problem, but instead of using the a priori approach, we wanted to use a posteriori approach. Because as we said, a posteriori approach will give you a set of optimal solutions, then the decision maker can maybe make a better solution instead of this solution. So how we started was that we started with a set of random solutions. The white circles are some random solutions. And we included the optimal solution found from the optimization study of our previous colleagues. Then we ran the optimization algorithm, the SB-MOO algorithm, and we found the Pareto front. So here you can see the Pareto front. It's a disconnected Pareto front. These are the set of optimal solutions, the blue crosses. The red square is the optimal solution found by the previous study by using the a priori approach. And decision maker, the same decision maker that chose this one, now could look at this set of optimal solution and find and select this optimal solution. And you can see that the optimal solution has been improved. So now look at the stress strain curve and see the difference. So on the top, you have the two stress strain curves for the two modes. The first one is mode 1, which is for peel, and the second one is mode 2 for shear. This is the previous study. The red line shows the experimental stress strain curve, and the dashed black line shows the simulation. F1 and F2 shows the error between these two lines. And this is our study, the new study. You can see that in mode 2, it's much more similar than the previous study, and the objectives also show better results. However, for mode 1, the difference was not that significant. But how did we run this study? As we said, we had to run finite element simulations to find the stress strain curve. And one of the properties of finite element simulations, especially if you want to have accurate results, is that they are very computationally expensive. So what do you mean by computationally expensive? So if you want to have accurate results, if you remember the elements I showed you in the previous slides, you have to select very small elements. And by having small elements, the number of elements will increase, and increasing the number of elements will increase the computational time. So each simulation for mode 1 in peel took around 30 minutes to 2 hours, and each simulation for mode 2 took 8 hours. So imagine a population of 40, you have to run 40 simulation for mode 1 and 40 simulation for mode 2. And that's for one generation of optimization. Then you have to run another 40 simulation for generation 2. And you have to run these simulation until your optimization algorithm converges. So this is very computationally expensive, and it might not be practical in real world. So if you want to do this study in the company asks you, he wants to do this study, then you cannot ask the company that like give me 1 month so I can run the simulations. So what's the solution for this? We'll come to solution later on. So let's look at the second example. The second application is in machining, and specifically in turning operation. So why did we select turning? So finite element simulations are mostly commonly used to simulate products and processes. And machining is one of the 5 main manufacturing processes. And here in our study, we focus on turning operation. But why did we focus on turning operation? Because we had a case study in Volvo cars that they want to optimize one of these processes in turning operation, which they call it operation 30. And in that operation, they machine the crankshafts of their engines. So they wanted to optimize this process. So we had to create finite element simulations, and we had to perform optimizations on that. So there are different softwares can simulate manufacturing processes, but DEFORM 2D or 3D is one of the softwares that we have the license in university. And you can use it if you want, if you're interested. You can simulate different manufacturing processes. So here in this figure, you can see the temperature simulation of the temperature along the interface in cutting operation. So here is a cutting tool, and this is a very small piece of the workpiece. The tool cuts the workpiece, and you can see the temperature distribution on the interface. And here you can see the result, the temperature after a specific length of cut. And you can see that the maximum temperature is 644 degrees at the tip, at the interface of the tool and the workpiece. So what we wanted to do is we wanted to integrate this finite element simulations into our multi-objective optimization. So the same thing, the finite element simulation will be placed in the fitness assignment part, but as we said, finite element simulations are very computationally expensive. So one of the solutions I said is automating this whole process. What do I mean by automating this process? So if you want to run optimization by finite element simulation, for each generation of optimization, you have to run the finite element simulation. You have to wait for the finite element simulation to finish. You have to analyze the results. You have to extract the results. Then you have to input the results to the next generation. You have to run the simulations, and this will continue. So there are a lot of manual work and a lot of waiting times that this might not be efficient, and it will take the computational time much more than it could be necessary. So it is not practical to perform simulation-based multi-objective optimization by running all simulations in each generation manually. So there was a need to develop a platform that can automate the whole process. So during my research, I developed a framework which automated the whole optimization, the entire multi-objective optimization of machining processes by finite element simulations. So this framework, as you can see here, eliminated the time spent performing the manual tasks during setting up the finite element model and multi-objective optimizations. It also enabled parallel computing. What I mean by parallel computing is that we had several workstations. We had a cloud of workstations. Then this framework could distribute different finite element simulations to different workstations or different computing stations. So by that, there were several finite element simulations were running at the same time. So here you can see that this framework consists of different modules. You have the initial DOE maker, the file generator, geometry generator, mesh generator. Each of these modules have input and an output, which the input is converted to the output. And the modules are different softwares. So for example, for mesh generator, I used what was the software? I used Most Frontier. Or for file generator, I used MATLAB. Or for simulator, I used Abacus. So there are the different softwares that can be used in this platform. And here you can see the automation part, which the distributor distributes finite element simulations to different parallel workstations. Each of them can run the simulation by their own. After they're finished, the results are automatically extracted. They are analyzed automatically and sent back to the optimizer. And this loop continues until the optimization algorithm converges. So in order to test this platform and to see how can we perform finite element simulation-based multi-objective optimization on this platform, I use a case study. Well, the case study was cutting AISI 1045 steel with a carbide tool in turning operation. So I had three objectives. One objective was material removal rate. This is obtained with a simple equation. And two other objectives were wear depth and the tool chip interface temperature. So you want to minimize the temperature on the interface between the tool and chip, tool and workpiece, and you want to minimize the wear depth. You don't want your tool to be worn out very fast. These two objectives were obtained by running finite element simulations in DEFORM. And I had 5 variables, 3 sets of geometrical variables, and 2 sets of process variables. So what I did was I had 4 different workstations and in total 20 cores. So I could run 20 simulations simultaneously. And each optimization algorithm, I had 40 initial populations, so 40 simulations needed to be run in the multi-objective optimization algorithm, and each simulation took around 5 to 10 hours. So 40 simulations for each generation, 20 running simultaneously, so each generation took around 20 hours. And the optimization algorithm converged after 17 generations. So in total, this study took around 2 weeks. And here you can see the results. The Pareto front in objective space. You can see material removal rate, the wear depth, and the temperature. And here you can see the different relation between the variable and objective in matrix plot. So as you saw, these were the 2 applications of finite element simulation in performing multi-objective optimization. But as we saw, since finite element simulation is very computationally expensive, usually running simulations on multi-objective optimization is not practical. So what we should do is use meta models. And we will cover meta models in the next video or in the next lecture.